Hey guys, Mr. McKinney here, just doing the fourth and hopefully last video in the position, velocity, and acceleration series. This one doesn't really have to do with position, velocity, and acceleration. This is just about other rates that can be related, so any related rates. Most derivatives that we talk about in this class are going to be dy dx, which talk about how y changes as x changes, so the rate of y with respect to the rate of x. So many problems that we do are going to be dy dx, and the vast majority of the practice problems you guys do are dy dx. But those are not the only rates that we can relate. We could do the rate of change of area with respect to radius, or the rate of change of volume with respect to height, or temperature with respect to pressure, or profit with respect to units. You can do pretty much anything with respect to anything else as long as you have equations that relate them. So let's do a couple of different examples other than just dy dx. So the first example we're going to look at is a balloon. A balloon, we're going to assume that it's a spherical balloon and it's being inflated, so it's being blown up. And we want to find the rate of change of the volume with respect to the radius. So we want to find the rate of change of volume with respect to radius. This is what we're trying to find, dv dr. Now in order to do that, we need to have an equation that relates volume and radius. For a sphere, we're going to start with volume equals 4/3 pi r cubed. Now if I want the derivative of volume with respect to radius, if I have a volume equation that is written in terms of radius, I can just take the derivative using our derivative rules. So the derivative of volume with respect to the radius would be 4/3 times 3 times pi times r squared. These 3's will cancel, so dv dr would be 4 pi r squared. So the rate of change of the volume with respect to the radius would be 4 pi r squared. So dv dr is 4 pi r squared. Now let's figure out what the volume would be changing when the radius is 1 inch. So going back to this formula, dv dr is equal to 4 pi r squared. And this question is asking is, what is the rate of the volume when the radius is 1 inch? And the way we would denote, denote that would be dv dr evaluated when r is equal to 1. So this is the notation. So dv dr evaluated when r is equal to 1 would be 4 pi times 1 squared. 1 squared is 1 times 4 pi would be 4 pi. Volume is measured in inches cubed. Radius is measured in inches. So we'd say that the rate is 4 pi inches cubed per inch. Do not simplify this to say inches squared. Inches squared is not a rate. Inches cubed per inch is a rate. So when the radius is 1 inch, the volume is increasing at a rate of 4 pi inches cubed for every inch that the radius increases. Now again, this is an instantaneous rate. So this is true when the radius is 1 inch. All right, this one says, what is the radius when the volume is changing at 780 pi inches cubed per inch? Looking at units can help us get an idea of what they're giving us. In this problem, inches cubed per inch, they're giving me the rate of change of the volume with respect to the radius. So they're telling me that dv dr is 780 pi. Now I have a formula for dv dr. If I go back to this slide, 4 pi r squared. So 4 pi r squared, and I want to know when that's equal to 780 pi. So what is the radius when this rate is equal to that? So I just need to solve this equation, divide both sides by 4 pi. So r squared is equal to, pi's cancel out. If I do 780 divided by 4, I get 195. And then square root both sides. it would be the positive or negative square root of 195. When we're dealing with a real world problem, we couldn't have a negative radius. And then I would want to write it with at least 3 decimals, so 13.964 inches. That would be the radius when the volume is changing at this rate. Notice that it's a rate because you've got inches cubed per inch. All right, let's look at a formula that has 2 variables in it. So I want to find the derivative with respect to either radius or height. And I've got the same formula for both of them. So I want to start with the same formula for both problems. V equals pi r squared h. Now, we're finding the derivative with respect to either the radius or with respect to the height. So for this first problem, I'm trying to figure out what is dv dr. For the second problem, I'm trying to figure out what is dv dh. So for the first problem, I'm going to say the derivative of the volume with respect to the radius. In this case, h is going to be a constant. We're going to assume that the height is not changing. So I can basically just rewrite this as pi h times r squared. And then when I take the derivative with respect to the radius, I'll take the derivative here, move the exponent in front, and drop it by 1. So it'll be 2 pi h and then r to the first power. So the derivative of volume with respect to the radius would be 2 pi h times the radius. Now, if I wanted to know the derivative of the volume with respect to the height, in this case, my radius would be constant. So the derivative, so we're pretending that the radius squared, this is all a constant. So this whole thing would be a constant, and I'm basically just taking the derivative of a linear function here. So the derivative of volume with respect to height would just be pi r squared. Since the derivative of h, I would multiply by 1, drop the exponent down to 0, so it's going to go away. So the derivative of volume with respect to height would be pi r squared. So note that depending on what variable we take the derivative with respect to, will change our answers. All right, the last thing, I want to give you guys a chance to try these would have been whiteboard problems in a regular classroom. So take a second to read through it, hit pause, and attempt these 2, and then I'll do them as examples. All right, so we've got a sphere, and we're looking at surface area this time, and the formula for surface area is 4 pi r squared. So the first one, find the instantaneous rate of change of the surface area with respect to the radius when the radius is 400 miles. So I want to find the derivative of surface area with respect to the radius. That's what it's asking for when the radius is 400. So I'm going to start with my formula. Surface area is 4 pi r squared. The derivative of surface area with respect to radius, I'm just going to multiply the 2 out front, so 8 pi r. I want to know the derivative of surface area when the radius is 400. So I'm going to do 8 times pi times 400, which would be 3200 pi. I'm going to leave it as just 3200 pi. Note that we're doing a rate of surface area versus radius. So my answer should be 3200 pi miles squared per mile. All right, and then the second half of this question is a lot trickier, and we're going to use this part to kind of help us out. The derivative of surface area with respect to radius is 8 pi r. So I'm going to write that over here. The derivative of surface area with respect to radius is 8 pi r. I'm going to make it a fraction over 1. We'll come back to this in a second. I want to find the instantaneous rate of change of the radius with respect to surface area when the surface area is this. So there's 2 ways that you can do it. I'm going to show you guys the more intuitive way first. So instead of starting with this formula, if I want to find the rate of change of radius with respect to surface area, I need to solve this equation for r. and then find the derivative. So if I start with surface area equals 4 pi r squared, I can divide both sides by 4 pi. So r squared equals SA over 4 pi. And then we'll take the square root. Without getting into too much detail, we're going to look at the positive square root in this particular problem. So I'm going to rewrite that as 1 over the square root of 4 pi times the square root of SA, which I can think about as 1 over the square root of 4 pi times SA to the 1/2 power. So if I want to take the derivative of the radius with respect to surface area, derivative of radius with respect to surface area, then I'm going to take the derivative here. This is just a constant, so it stays out front. 1 over the square root of 4 pi times 1/2 times SA to the negative 1/2 now. So then I can just plug it in. dr over dSA would be 1 over 4 pi, the square root of 4 pi times 1/2. SA to the negative 1/2 power would be 1 over the square root of surface area. So now I can just plug in the number that it gives me. So 1 over the square root of 4 pi times 1/2 times 1 over the square root of that number. And that would give me a very small decimal, 1.2934 times 10 to the negative 4. And this would be miles per mile squared. So this is one way that you can get to your answer. The other way that you can do it, and it'll give you the exact same answer, is think about this formula and then flip it. You can flip it so that the rate of change of the radius with respect to the surface area is 1 over 8 pi r. Now in this problem I don't have the radius, I have the surface area. But if I plug in this surface area into this formula for radius, and I get that radius and plug it in here, I'm going to get the exact same value. So there's two ways to get the answer, and we'll be coming back to these tricks later on throughout the course. But one thing that you can do is you can flip a rate. So if I have dSA over dr, and that's 8 pi r, I can flip it and make it dr over dSA is 1 over 8 pi r. Again, we're going to be coming back to stuff like this throughout the course. Hope this one helped.